everyone, welcome to the morning session of QIQT. And although there is no need for introducing Professor Bhanu Das, but just as a formality, let me just introduce him. So he is a professor at the Department of Physics in School of Science at Tokyo Institute of Technology, and also the director of Center of Quantum Engineering Research and Education, TCG Crest. He's a fellow of American Physical Society and famous for his work in CP violations and of all in many other frontier areas in atomic molecular physics and particle physics. And his research interest is in currently quantum computing and relativistic many-body theory of atom molecules and high-performance computational studies on atoms and molecules. And he is one of the frontier person in this area. And he will be talking about computation of relativistic and correlation effects in atomic system using quantum annealing. So I leave to Professor Das. Yeah, you can first share.
Thank you very much, Dr. Shambhodashanal, for your very kind words of introduction. Let me, yes. So can you all see my, sorry, listen. So can you all?
You have to share your screen.
Okay. Sorry about that. Yeah, just a minute. Just a minute, please. Yes, so the is it okay now?
No, not yet. I can't see.
Oh, I don't know. I thought I've shared it. Is it okay now, or is still
no?
time?
I don't.
So what? Yeah, I mean, I went to share screen, and then there were different options which I've clicked. Multiple. Okay. Yeah, sorry. I don't know what's going on when I've shared it, but.
It will probably give you all these screens you have open and.
Yeah. I mean, one.
Usually the first one is by default the whole desktop, but you can choose.
Sir, you can unshare your slides and again share.
Okay, let's see. Let's do that. Yeah. Is it okay now? Okay.
No, not yet.
Yeah.
I don't see.
Yeah, actually, I've sent it by email to both Professor Panigrai and to QIQT.
Yeah, but yeah, that is one way, but you may not have the control of going back and forth.
Okay. Yeah, I don't know. Okay, just a minute. Let me just.
Okay.
Yeah, just 1 second. Yeah.
I got the reply from working.
So the talk is open. How do I share the screen? Share. Yeah. Yeah, it's fine. Yeah. So someone can share it. You want to share? Yeah, with the audience. Yeah. You want to share this one? Yeah. Talk is open. Okay. This is the only option. I see. Yeah. Maybe I think you can open the talk at your end, and that might be the best. I guess I'm really sorry about it, but
Yeah, can this QIQT email ID?
Yes, we are doing that.
We are doing that.
oh yeah, sorry.
We are
Oh
doing that.
yeah, yeah.
Great.
So shall we? Yeah, sorry, I didn't have my headphones. So shall we? I can try another laptop, or if you can open the talk, that might be better. Hello.
Yeah, okay. I think this somebody is doing that. Opening.
Okay,
Yes,
okay, yeah.
because we
Okay.
release the page for a minute.
Yeah, sorry about that. So let me also try to see, I'll use another laptop also.
ये वाला
I think there is some permission. That has to be granted for this.
Yeah.
Yes.
Yeah.
How do you open this?
My,
I think
इसको full screen कैसे कर
you want to open it from your
Yes, yes.
share तो मैं कर full
or
screen
you can send it to
दिख रहा है यहाँ पे तो दिख रहा है ना ये चेक कर
You. Yeah, I think it is showing now. You can control it.
okay.
Now you can-
So yeah, I can't see the slides. Can you?
share तो कर दिया मैंने sir can you see the slides now
No, I can't. I mean,
अपना QIQT Zoom खोलो यहाँ पे जाओ अच्छा समझ इसका मैच ठीक है
yeah, now I can. Yes.
Oh, yeah.
Okay, so then, yes. So shall I start now? Okay.
Yes, sir.
Yeah. I mean, I'm really sorry for this, some, problem in sharing with my laptop. Really sorry again. But, so let me first of all start by thanking Professor Panigdhai and the organizers of QIQT. And I'm grateful for them inviting me to give this talk. The focus of my talk is going to be how one can calculate atomic properties which arise from relativistic effects using quantum annealing. Now, since it's an atomic system, there will be correlation effects. So I'll be talking about how one can compute relativistic and correlation effects in atom using a quantum annealer. Quantum annealing, as you all know, is the second paradigm of quantum computing, gate-based being the first paradigm. And it was theoretically formulated coincidentally in the Department of Physics at Tokyo Institute of Technology, which I'm still affiliated with, by Professor Nishimori in 1998. And he gave the first, theoretical formulation in its current form. And just a year after that, D-Wave in Canada decided to build a quantum computer based on that theoretical idea. And D-Wave went on to become the first quantum computer. It now is the world leader in quantum annealers, though other companies have and research groups are trying to build quantum annealers as well in different countries. So let me move on to the next slide, please.
Sir, you can change it your by sir.
Oh, okay. Okay.
Hit the space button.
Okay, yeah, sorry. Yeah. So how do I? Okay, can I? Yeah, I just want to go back. Okay, I'm going. Let me just. Sorry, I don't know. I mean, not this one, but the next, the previous one.
Sir, you can hit the left arrow key, so you will go back. So
okay.
Yeah.
Okay. Sorry.
So is that fine now?
Yeah, it's fine. Yeah.
Okay. So yeah, thank you.
Thank you. Yeah. So yeah, so these are my collaborators. The first person, Vikrant Kumar, who got his MSc in physics from, or rather BSMS in physics from IISER Kolkata last year. He was the driving force of this work. So the computations have been done by Vikrant, and of course, he has an excellent understanding of quantum annealing, and the results that we've got were mainly due to Vikrant's efforts. The four of us from, or actually five of us from our center. And in addition, we've collaborated with Professor Sugisaki, who's now at Keio University in Japan, and Dr. Ken Dial, who's one of the world's leaders in the relativistic theory of atoms and molecules. I don't know. Okay, so again, I'm having difficulty. I don't know what's going on.
Hello, sir.
Yeah, so I'm not able to move. So if I, so the right button should, no, it doesn't seem.
I
to
think
be-
forward is space and the left button is back.
Yeah, so,
So you press the space button.
oh, okay, yeah, okay. Yeah, yeah, okay. So the outline of the tone. Oh, yeah. Yeah. So the outline of the talk, I'll first give a brief introduction to atomic systems. By that, I mean neutral atoms and atomic ions. And then I will talk about relativistic effects in atoms and also about the mean field and correlation effects. And then I'll talk about fine structure splitting in atomic systems. This is a splitting between energy levels. And this is a genuine relativistic effect. I mean, it does not happen in the non-relativistic limit. So if one wants to study the interaction between, or the interplay between relativistic and correlation effects, then this is probably one of the best properties to look at. And then I'm going to talk about basic ideas of quantum annealing with reference to D-wave hardware, because we've used the D-wave hardware for our computations. Now, for doing these computations, we have used an algorithm called the Quantum Annealer Eigensolver. And this can compute ground state energies of atomic systems. And we have sort of adapted that to calculate the ground state and the first excited state using atomic symmetry. And the ions that we have chosen are boron-like ions. So boron has 5 electrons. The outermost electron is a p electron. And that has fine structure splitting, because if you have a p electron, then the orbital angular momentum is 1, the spin is half. So that splits into 2 levels, total angular momentum half and 3 halves. And that difference is the fine structure splitting. Okay, so yeah, okay. So so let me just explain how relativistic effects can arise in atoms. Now, if you start with a non-relativistic Hamiltonian, that's the first equation that I've given. So you see that the second term describes the interaction of the electrons with the neutrons, and that depends on the nuclear charge. Of course, you also have the electron-electron interaction. Now, the motion of the electrons is due to its interaction with the, of course, it has its own, kinetic energy, but it's also affected largely by its interaction with the nucleus and other electrons. Now, the nuclear electron interaction is an attractive Coulomb interaction, and that depends on the nuclear charge Z. Now, the velocity of the electrons will depend on the nuclear charge. So if Z is large, the nuclear charge is large, and then the velocities will be large. So if the nuclear charge is very large, say if it exceeds 20, 20 is not very large, but relativistic effects will start showing up. And for higher nuclear charges, the relativistic effects will be very strong. So in order to study relativistic effects in atoms, one chooses heavy atoms or heavy ions, that is, atoms and ions with a large nuclear charge. So, but once you take relativity into account, then the Hamiltonian is no longer the usual Hamiltonian that I have written in the first equation, but it becomes the Dirac Hamiltonian, the many-electron Dirac Hamiltonian. So the p square over 2m gets replaced by c alpha dot p plus beta mc square. That's the Dirac Hamiltonian. And then you have the nuclear charge plus the Coulomb interaction between electrons. Now, that is what we call the Dirac-Coulomb Hamiltonian. And that will describe the properties of, that will describe many atomic properties for relativistic systems. But sometimes we need corrections to that. That is, you see the Coulomb interaction, the last term, E square divided by Rij, that's there both in the non-relativistic case and the relativistic case. And that is essentially a non-relativistic interaction. Now, that also has relativistic corrections, which I've given below as HB, that is the bright interaction. So electrons, so the Coulomb interaction is basically a static interaction. So we assume that the electrons are at rest and they interact, but electrons are actually moving. So when they're moving, there's a current and the two currents can interact. And that is the first term. And also the assumption is that the photons that are interchanged between electrons are transmitted instantaneously. That is not the case. There is some retardation, and that's given by the second term. So here alpha and beta are 4x4 matrices. So the relativistic Hamiltonian is very different from the non-relativistic Hamiltonian. So of course there are other corrections, but usually they're not as important as the bright correction. Okay. Oh yes, okay. Right, now let me show the connection between atoms and molecules and quantum annealing. Basically, let me explain how one can use a quantum annealer to calculate atomic properties or molecular properties as well. Now, to see that, let's start with an energy functional, epsilon, that I have. Okay, so there's a typographical error. The first term should be the expectation value of the Hamiltonian, which is missing here. So it's bra psi h get psi. And if you want, and then you have a Lagrange multiplier to normalize the wave function. So what one does is that one can, or maybe this is 1 second. I think maybe I'm missing a. I think I need to go back. I think so it's the left arrow to go back, right? Okay. Hello?
Yeah, I think so. I think it's the left arrow.
Yeah. Doesn't seem to be good. Oh, yeah, I don't know.
Not working?
No, I don't know.
Okay. Can someone from the team, QIQT team, see that?
Can I go to the previous slide, please? Okay. So this is the slide. So so the previous slide had the relativistic Hamiltonian to describe atom. Now let's look at the wave function of atomic systems.
Mhm.
So if you, to understand how to write the wave function for an atomic system, so let's take a simple atom like helium, where we have 2 electrons. Now, the simplest configuration is we have 2 electrons, as shown in this figure, and the wave function for that I call phi 0. So we have 2 electrons, one is up and one is down. Now, this is called the mean field representation, because here each electron is moving in the potential of the other electron. So you can have 3, 4, 5, any number of electrons, n electrons, and each electron will move in the potential of n-1 electrons. So that is the mean field picture. Now, then you start taking into account the interaction between the electrons, the Coulomb interactions. Now, when that happens, one of the electrons, say one of the 1s electrons here, can be excited to the 2s state, and you'll have a 1s 2s configuration. Then both the electrons can be excited, and you can have the 2s2 configuration. So now these states, phi 0, phi 1, phi 2, etc., they form a complete basis set. So a complete many electron basis set, and a general wave function psi, which is given below the diagram, can be written as a linear combination of these phi's, phi 0, phi 1, phi 2, and so on. So this kind of a wave function is called the configuration interaction wave function, because it takes into account the different configurations arising from the Coulomb interactions, you see. Now, this wave function is an eigenstate of the relativistic Hamiltonian H, and that depends on 3 quantum numbers: the total angular momentum J, and the magnetic quantum number M associated with it, and parity. So the energy depends on J, the J value, and the parity value. Now M, it doesn't depend on the M value. For a given J, all the M's have the same value, you see. Now this wave function, psi as a function of J, M, and pi, can be a ground state or an excited state. So it will be an eigenstate of the atomic Hamiltonian. Now if we consider this expression, the energy function in epsilon, which again, I think, there's a typographical error. So it's the expectation value of the Hamiltonian, that's the first term, minus lambda psi, which is for normalization. So here, if we take this and write the wave function as a linear combination of the states, the basis states, then the energy functional will depend on the coefficients. So if we minimize the energy functional with respect to the coefficient, we will get the matrix equation for the Schrodinger equation, or rather the Dirac equation here, which is HC equal to lambda C. And lambda here, which was a Lagrange multiplier, is actually the energy of the system, you see. So so one can solve this matrix eigenvalue problem, HC equal to lambda C, on a classical computer. You can diagonalize the matrix, and the lowest eigenvalue will be the ground state, and then you can get the excited states also. So this is how this is one way of getting the wave functions and the energies of an atom. And the important thing to note here is that the energy depends on the J value. So we can find the wave function for different J's, and therefore the energies for different J values, and we can take the difference between them. And that is what the fine structure splitting is. That is, for the same L values and the same S values, the same orbital and spin angular momentum, we have a total angular momentum, which could be J and J prime, and the energy difference between them is the fine structure interval. Now, non-relativistically, J doesn't split into 2 states, but relativistically it does. And it arises from from the relativistic effect shown in the Dirac equation and the bright interaction and so on. So what we'll do in this talk is to present the fine structure splitting for boron-like ions. That is, boron has 5 electrons, systems with 5 electrons, but different nuclear charges. And we will do that using quantum annealing. And we will compare our results of quantum annealing with results on a classical computer and also high precision experiments. Now, the ideas that I've just presented, that lambda, which is the Lagrange multiplier, actually is the energy. This idea has been used in the quantum annealing algorithm to find the fine structure splitting. Okay, so the next slide, please. Yeah, okay. Now, now that you've seen how these calculations are done on a classical computer, we will talk about quantum annealing now. And I'll show the connection between atoms and molecules and quantum annealing. Now, and we need an algorithm for that. That algorithm is called the Quantum Annealer Eigensolver. That was proposed about 3 years ago. So here, once, like in the case of configuration interaction for atoms, one starts with an energy functional epsilon, which is, again, the first term is not right. It's the expectation value of the Hamiltonian in the state psi. And then we have the Lagrange multiplier for normalizing the wave function. So that is written in terms of the matrix elements of the Hamiltonian in the many-electron basis phi I and phi j. So HII is the diagonal matrix element minus lambda CI square minus HIJ, the off-diagonal term, times CICJ. So the coefficients of different configuration states. So this is the basic energy functional which we had used for our atomic calculations. This is also the starting point of the quantum annealer eigensolver. Now, to use it on a quantum annealer, it has to be expressed in a form called QUBO, that is quadratic, I think, unrestricted binary optimization. So I'll explain what the QUBO form is. So the QUBO form is given below in this equation. I think the equation for F subscript Q. So you can see that it is QII times small qi and capital QIJ, small QIQJ. So the energy functional has to be written like that for it to be used on the D-wave machine. So we can see the connection between the energy functional used in atoms, which is epsilon, and FQ, which is used in the D-wave quantum annealer. You can see that the QII is like HII minus lambda, and QIJ is like HIJ. And and you have a quadratic term for CICJ, and the CI square will be QI. We can see the connection very soon. Now, the idea is to provide the annealer values of QII and QIJ, and then vary the small q's, which can take values of 0 and 1. And by varying QI, QIJ, we get the minimum value of F. So we minimize the functional F by varying the cubes, the small QI and QJ. So the way it is done is that in an annealer, we choose a time interval here. The annealing is from time 0 to time capital T. Now, in this interval, the Hamiltonian changes. So the starting Hamiltonian, so the general Hamiltonian has the form P as a function of T, sigma X, sum over I, and QT, HT, and HT has an Ising Hamiltonian, is the Ising Hamiltonian in terms of Z components. Now, if you look at the Hamiltonian at time t equal to 0, it is simply sigma X. And the final time, it is the Ising Hamiltonian H T, okay. So what is done is that so we start with the we start with states that correspond to eigenstates of sigma X, and we end up with the eigenstates of the Ising Hamiltonian, which is, you know, either 0 or 1, you see. So the system actually is allowed to make a transition from time t equal to 0 to time t equal to t, and the Hamiltonian changes accordingly. And so what we end up with is a state which is made up of either 0 or 1. Now, how does one change from the atomic energy functional to the D-wave energy functional? Now, that you can see the second last line, that's what I've written here, is that the coefficient C in the atomic energy functional, they are transformed to Q. So we carry out a transformation. Now, C's are the coefficients, so they can have any value from -1 to +1. So that's a discrete set. Sorry, that's a continuous set. And then we transform them to Q's, Q alpha subscript n, so that Q can only take two values, 0 or 1, you see. So we carry out such a transformation. So all the C's are transformed to Q's. And the last equation, FQ, is the functional that is used in annealing. You can see that the first term is quadratic, it's QQ. There's a QN alpha and a QM beta, and you have a quantity A, which depends on the Hamiltonian matrix elements, and then you have the second term, which is just linear in Q, because, well, I mean, if you compare with the atomic term, it is Ci squared, but if it's like Qn square, you know, or Q alpha n squared, that will be, you know, that will simply be Q, because the value of Q is either 1 or 0. So in that case, Q square is the same as Q. So you have a quadratic term, you have a linear term, and then you have another term C, which is just constants, you see. So it's important to remember that when we make this transition from epsilon to F, we are, now epsilon has, you know, H matrices, which could be of the size, say, n by n. But when we make this transformation from epsilon to F, then we are dealing with matrices which are of this, or which are nk times nk. You can see the double summation. The first is overall the base B represents the basis set, and then there's a second summation over k. So the size of the matrices that one deals with when you make this transformation becomes larger. From n by n, it becomes nk by nk, you see. So then what one does is one varies the small q's, the qubits, till FQ has been minimized, you see. So this is essentially what one does. And so there is a interesting connection between how one minimizes an energy functional for an atom and how one would do that in a quantum annealer. So we just have to change the coefficient C's to qubits, Q. So that can take the value of 0 or 1. So of course, the price you pay is that the matrices that one deals with, their size increases. Okay. Okay, so the next slide, please. Okay. Yeah, okay, sorry. Okay, yeah. All right. So what I have here is the workflow, which tells you how the computation is done in a D-wave quantum annealer. So we start with our atomic Hamiltonian, which is the Dirac Coulomb plus the bright, so which is what I call HDCD. So we compute the matrix elements of that Hamiltonian, and then we have this energy functional. You remember that it depends on the Hamiltonian and the Lagrange parameter lambda, which is actually the energy lambda. So once we have the energy functional, then we construct the QBO function, FQ, for the quantum annealer. That is what I just explained in the previous slide. So when you go from epsilon to FQ, you'll be dealing with matrices with larger sizes. You know, I mean, K is typically 10. So the dimension of the matrix, you know, will increase by 10 times 10. So, but, you know, so that's what we do. But remember that the QBOs also, the FQs also have the qubits in them, which one, yeah. Now, the QBO that is constructed will have to be optimized in the D-wave machine. So we used D-wave Advantage 5000Q, which was you know, provided to us through METI grant. And now this may seem easy, but actually it is a little challenging because we have to do embedding here. What I mean is that you remember that both in H and, I mean, both the energy functional and the QBO functional, we have matrices like Hij and you know, Aij and so on. So that means the qubits are connected. And so the D-wave has a certain architecture which one has to understand. And then the QBO functional has to be adapted to that architecture. That's not very easy. Meaning it's not very straightforward. It's not like a classical computer where you give your input and you get an output. So there we don't need to understand the architecture of the machine too much. It helps, of course. If you know the architecture and you take advantage of it, that's obviously you know, it's going to be beneficial. But for a quantum annealer, it's actually absolutely necessary. It's absolutely essential to understand the architecture. So we adapt the QBO energy functional to the architecture of the D-wave, and that's what we call embedding. Now, once we do that, we start the annealing. That means going from 0 to some time t. So the Hamiltonian changes in between. And so we do the annealing till for a certain period of time, till the energy functional or the QBO functional is minimized, you see. Now, this has to be repeated many times. Okay. And for the atomic calculation, it is particularly time-taking because we start with an initial value of lambda. So we want to calculate the energy, which is lambda. So we don't know what it is. So we give it an initial value based on physical considerations. And then after what we call one repeat means we do the annealing about 1,000 times. So after 1,000 anneals, we stop and look at the value of lambda, and we update it. And then we keep on doing this. So after many cycles of annealing, we look at the value of lambda. And we look at what the minimum value is in these annealing cycles. And we take that as our minimum energy. So, of course, the energy that, okay, for that, of course, the qubit configuration that gives the minimum energy, the minimum value of energy, will have to be then changed to the atomic wave function, because we had changed the coefficients to the qubit structure. So from qubit, we'll have to go back to the usual atomic wave function. So from the qubit wave function, we construct the atomic wave function, and then using our Dirac-Coulomb Hamiltonian, we calculate the energy, you see. So the crucial steps here are the construction of the QUBO, that is to convert the atomic energy functional to the energy functional that is compatible with the QUBO structure of the D wave. And then we have to embed, that is, before we can anneal, we have to adapt the functional to the architecture of D wave. And then we do the annealing procedure many times. That is, we allow it to go from zero, some initial time, to final time. And we repeat that many times. And at the end of each anneal, we look at the energy value. And after many such anneals, we get the lowest energy. And then once we've got the energy, we look at the corresponding qubit configuration, that is the wave function, that we change to the atomic structure that I had mentioned earlier. And then using the atomic wave function that we get from the qubit wave function and the atomic Hamiltonian, we calculate the energy. So this is basically what is done. So the next slide, please. Okay, now I can tell you how we have done a calculation. So what I have explained is that it is possible to calculate the energy, the ground state energy, using the D wave quantum annealer. Now, the system that we took is boron-like ions. Boron has 5 electrons. And so we took different boron-like ions to do the calculations. Okay. Now, each of them has a ground state. I mean, the electronic configuration is 1s2, 2s2, 2p. So the L value, the orbital angular momentum, is 1. And the S value, this total spin angular momentum, is half. So the total J value can be half or 3/2. So they correspond to 2 different states relativistically, you see. So that I've shown here. And so what we have done is that we have used the annealer to calculate the energy of J equal to half and the energy of J equal to 3/2. Now, this is a very small quantity. This difference is a very small quantity. And if we do them together, then it's very hard to tell which is which, because the difference is so small that that we might get 3/2 to be less than energy of half. So what we do here is that we take advantage of atomic symmetry. That means if we take a particular wave function, that wave function includes configurations of a given angular momentum. So in other words, when we take the wave function for J equal to half, we only have contributions from J equal to half. And when we have energies from 3 halves, when you have the wave, when you have the state from 3 halves, it only has contribution from 3 half states. So these states will not appear together. So we have taken all possible, I mean, a lot of j equal to half states and a lot of j equal to 3 half states, and then done annealing 2 different times. So the minimum that we get for each of these calculations, one of them will correspond to j equal to half, and the other will correspond to j equal to 3 halves, see. So we get 2 different energies, and we take the difference, and that is how we get the fine structure splitting, you see. So we take advantage of atomic symmetry to do 2 different quantum annealings, and then look for the lowest energy state in each case, you see. So now, what I should tell you is that when we do the j equal to half state, the size of the atomic Hamiltonian that we deal with is 9 by 9. But when we change it to the cubo form, it becomes 90 by 90. That is, when you change the coefficients to qubits, the size increases, it becomes 90 by 90. So there's a 10-fold increase. And for j equal to 3 halves, it was 16 by 16, but after changing it to the cubo form, it became 160 by 160. So when we did the annealing, we had to deal with matrices that were 90 by 90 and 160 by 160, not really large by the standards of classical computation, but it's still early days in quantum annealing. So this is still, fairly large by the standards of quantum. Oh, okay, sorry. Sorry, the previous slide, please. Okay. Yeah, sorry. So you see, one was 90 by 90 and the other was 160 by 160. Now, when we make it compatible with the architecture of the annealer, there one has to be careful. So what we did was that we broke the cubo into 3 parts. So 90 by 90, so we had to deal with each part that was 30 by 30. So instead of doing annealing for 90 by 90, we did annealing for 30 by 30, 30 by 30, 30 by 30. Because each of them involves a lot of qubits because of the architecture. So a 30 by 30 matrix actually involves 110 qubits. Okay, and so we chose 3 such what you can call subqubos, and each of them corresponding to 110 qubits, and we did the quantum annealing. And for the 3 halves, it was 160 by 160. We broke it up into 4 parts, each 40 by 40, and 40 by 40 means 180 qubits. Okay, so this is essentially what we did, and so the next slide, please. Okay. Yeah. Okay, so these are the results that we got for boron-like ions, the fine structure. And we chose 4 ions because for these ions, there was experimental data. So the ions that we have chosen is calcium 15 plus, iron 20 plus, krypton 31 plus, and molybdenum 37 plus. So molybdenum has a nuclear charge of 42, and the correlation effects are quite strong there, you see. So the first result, that is what we call rel CI, that is relativistic CI, So these are atomic calculations done on a classical computer. Okay. Now the second and third, we've written simulation in hardware. They correspond to calculations using the quantum algorithm called Quantum Annealer Eigensolver on a classical computer first, and then on the D-Wave hardware. And finally, we have the experimental results. You can see that the agreement is very good. Now, when we compare the hardware results with experiment, then the agreement on the average of these 4 ions is close to 99%. So that means the error is about 1%, you see. Now, when we compare relativistic CI configuration with simulation and hardware, that's also very good. That's even better, actually. I mean, so now this actually was beyond our expectation, you know. And so this is the fine structure splitting, the energy difference, which we got by doing 2 different quantum annealing computations. Okay. Okay, the next slide. Yeah, okay. So what I showed you in the previous slide were results of fine structure splitting. That is the difference of 2 states. Now, how do the individual energies compare with with the classical computation, which we use as the benchmark? So we have chosen one particular ion, that is boron-like krypton. And so the first column is the relativistic CI calculation in atomic units, that is Hartrees. And then we've given the comparison between simulation and relativistic CI and hardware. So you see the agreement is very good. It's about 0.00007 and 0.00053%. So that means the classical computation, if you use that as the benchmark and compare with the results of the quantum annealing eigensolver, either using a classical computer or the D-Wave hardware, is very good. I mean, the individual energies match very well. Okay, so I've not given a hybrid sampler, which I think is anyway. So now I'll go to the last slide, which has the conclusions. So the next slide, please. Yeah, okay. So here I'll state our conclusions and outlook. So we have performed computations of the fine structure splitting in boron-like ions using the quantum annealer eigensolver using the D-Wave 5000. So we have obtained an accuracy of 99% compared to high precision spectroscopic measurements of the fine structure splitting of these ions. Now, if we compare with classical computations, the agreement is even better. But I thought, let's take the most accurate or the most reliable value that's available. Okay. Now, how did we achieve this kind of accuracy? Okay. Now this is a physics problem. And so the physics has to be incorporated very well. So, if we had started with a non-relativistic Hamiltonian with some relativistic corrections as a perturbation, the results would not have been so good. So what we did was that we started with a full relativistic Hamiltonian, that is the Dirac equation supplemented with the Coulomb interaction. Okay. Now that we felt was not enough because this is purely a relativistic effect. So although the Dirac, if you use the Dirac term in the Hamiltonian, it accounts for all the one electron effects very accurately, but the Coulomb interaction, which is very important for atoms and molecules, that is essentially a non-relativistic effect. So that has to be corrected in any relativistic framework. So, I mean, you can't treat the electrons as static and consider the interaction between them, especially if you're doing a relativistic calculation. So we added the leading order relativistic correction to the Coulomb interaction, which is the bright interaction. It's 4 orders of magnitude smaller than the Coulomb interaction, but it's important when we do relativistic calculations. So we try to get the physics right. And here, there's another subtlety. We are looking at 2 different states, j equal to half and j equal to 3/2. Now, if we were to do 2 different calculations classically, and then take the difference, that can lead to errors. So what is important is to do the calculations using the same set of single particle wave functions. Now that, of course, is there's some technical reasons for that I'll not get into. So we made sure that that the physical effects were included as accurately as possible. And then the workflow of the QE algorithm, we had to take some special care of that. I mean, the previous workflows had not taken into account some of the physical considerations. That is what we tried to do. So, when you do the workflow, I mean, you have to do the adaptation of the QUBO functional to the architecture of the quantum algorithm. So those things we tried to do as accurately as we could. And QIQT played a very important role in doing all this. And in terms of our outlook, I would say this is the first step for us in carrying out high accuracy quantum annealing computations of atomic quantities, which can have a wide range of applications. So atomic physics is used, in many different cases, for fundamental physics, for plasma physics, for astrophysics, and so on. Now, our main interest, of course, is in probing new physics beyond the standard model of particle physics. And there the effects are relativistic in nature. So we've done a relativistic calculation. And so this is a proof of principle work. And we intend to work on heavier atoms and molecules in the future. So thank you very much. And I'm really very sorry for the problems we had with my laptop. I'm sorry about that. Thank you.
Okay, thanks, Professor Das, for this very illuminating talk. So let's open for questions. Audience, is there some questions? Yeah, you can ask just directly.
I have a question. A small doubt, how the D wave, for D wave, the function FQ was written. Like you are making a correlation from like C, the coefficients in the wave function, to Q, the qubit states, right? 0
Yes.
or 1.
Mm-hmm.
So that C is a continuous function, like
Yes,
continuous
yes.
value from -1 to 1.
Right.
Where Q is 0 or 1.
Mm-hmm.
So how that like correspondence is made?
Yes, yes. I mean, those details are not given. That is a technical thing. I mean, that needs some discussion. I'll be happy to send you the details of the equations, how we arrived at this. There are others also who've sort of done this. Ours is a little different, but yes, that's not a straightforward thing. I mean, it's a mathematical thing, but okay. Maybe it's best if I just, if you just let me know your email address, I can send the details to you.
Sure.
Yeah. Thank you.
Thank you.
Okay. More questions?
I have one question. Can you hear me?
Yes, yes, I can hear you.
Yes. Thank you for your talk. Can we use quantum annealing eigensolver in the Heisenberg picture? Because in case of 100 photons, I have to write 100 terms in the Hamiltonian and then find eigenfunctions of 100 photons.
So you want to find the lowest energy of that system, right?
Yes.
I haven't thought about it, but so the let's see. So can we go back to the slide where I had the connection between atoms and molecules and quantum annealing? Yes, please. Yeah, please keep going back. Please keep going back. No, the one before this. No, after this. Yes, please go ahead once more. Okay. Yes. Yeah. So you see the so the crucial thing here okay, maybe the previous slide, let's see. Yeah, can we go to the previous slide, please? Yeah. So you see, I mean, I have written psi just below the picture, psi as sum over I Ci phi I. Now, if we can do that for your problem, that is, if you can write a general wave function, which is a linear combination of, in this case, it would be some basis states. So if it's, for photons, you probably will have Fock states as your basis states. So if you can write a general wave function, psi, which is a linear combination of a many-particle basis, then I think it should be possible. So in other words, what would your basis be for photons? The system that you're thinking about, what would be your many-particle basis states?
I mean, can we use the second quantization? Because you're talking about the Schrödinger picture, so it complicates when I am considering 100 photons or more, right? So in case of Heisenberg picture or second quantization, I will I do not have to write like or find wave functions of 400 photons.
Yeah. Now you see, I could have also used second quantization here. I mean, when I go from phi 0 to phi 1, I'm basically applying creation and annihilation operators. You see, like for example, if I go from phi 0 to phi 1, I would have to apply a 1s destruction operator and a 2s creation operator. So that I don't think first or second quantization is the problem, but the problem is to identify the quantum annealing eigensolver is in the language of wave function. So if you can write a wave function conveniently in terms of a many-particle basis, then I think it's possible. It doesn't matter whether it's first quantization or second quantization, because what you should be able to compute are matrix elements of the Hamiltonian. That is necessary.
Thank you.
Okay.
Okay. I have one quick question. So I'm just wondering that how scalable are these methods? Like for this is a 5-electron system, if I understand right, and you can do it for even more complex problem. But what if I want to do it for a much larger system? The kind of things that we are interested in in condensed matter. So that was one part of the question. The other part is that in this, the idea is to start with a product state. Then you do annealing and eventually land on the as close as possible to the ground state, right? So if the ground state has some non-trivial entanglement structure, like, so is it a good method to do that?
Yeah. Now, I mean, there have been some remarkable work on condensed matter systems recently using the D-wave system, using coherent quantum annealers, where they have taken spin systems, many body spin systems, and got some remarkable results, Hibble-Zurek mechanism and so on. Now that, of course, doesn't use this algorithm. So the algorithm would depend on the problem of interest. So whereas this problem is okay for this system, it may not be appropriate for other systems. Now, having said that, I didn't talk about entanglement, but you see, atomic and molecular systems are highly entangled systems, or they're entangled systems. The degree of entanglement varies. Now, if you look at the wave function I've written here in this slide, psi, which is a linear combination of different many particle basis states, Ci phi I. Now, the Ci here tells us about how strongly correlated the system is. If the maximum value of Ci is 1, if Ci is, if some of the Ci's are close to 1, that means the correlation is strong. And correlation is directly related to entanglement. That has been discussed. So what we are dealing with here are entangled systems. So so it doesn't matter how strong the coefficients are, I mean, how large the coefficients are, this method will work. So this method is capable of treating strong entanglement, strong correlation meaning strong entanglement. I didn't talk about that explicitly. But however, for the condensed matter systems that you may have in mind, this algorithm may not be the best. So I can send you the two really remarkable work by the same group, Andrew King and his collaborators in D-Wave. One was in Nature Physics, September last year, and one was in Nature last month, where they have applied the D-Wave quantum annealer to look at various aspects of many-body effects in condensed matter systems. So I can't give a sort of a general answer to your question, meaning whether this can be applied to condensed matter systems or not. It will depend on the problem, and it will depend on the architecture of the quantum annealer.
So I was kind of also like curious about this general point that the annealing, if I think of the physical system, the physical device that is the computing device, so it has the processes that you are allowed to do is cooling and some unitary evolution and probably some measurements. I don't know enough about these annealing devices. So if I start with a product state, how do I generate an entangled state by doing these 3 steps, 3 kind of process? So that is what I was wondering about.
Yeah, I mean, okay, now before I answer that, I mean, I forgot to answer a question about scalability, you see.
Yeah.
Now, scalability is a problem with this method. I mean, we have to look at newer kind of annealers that are being built in different places. Now you see, you know, as I told you, I mean, we started with, I mean, for these two cases, if we do it on a classical computer, it is 9 by 9 and 16 by 16. But if you do it on a quantum annealer, it increases tenfold, you see. So the qubits that we need, you know, increases sort of I mean, if not exponentially, it increases quite significantly. So, so that means the performance also will slow down as the system size increases, you see. So there, I think we'll have to think of cleverer methods. I mean, and also using the architecture. So I'm afraid this quantum annealing eigensolver, though it has you know, its connection with atomic and molecular calculations, that part is very appealing. It may not be very scalable, but it's something that has to be explored. But yes, there are other kinds of quantum annealing eigensolver that scale quite well, actually. But this about quantum annealing eigensolver, it's an open question. Now, then about your yeah, about the how are entangled states, you know, produced during quantum annealing. See, what you're doing is that you're driving the system from you know, individual qubits as you do the annealing. So during the annealing, you will get states. I mean, if you look at the Hamiltonian and look at the structure of the wave function as we proceed with time, because you know, you have many qubits, okay, and that can produce you know, entanglement, because I mean, if you look at the structure of the wave function that we use here, these are entangled wave functions, you see. So the dynamics you know, of the qubits will produce entanglement as one drives the annealing protocols. I don't know if I've answered your question.
Yeah,
but...
yeah, I get that. But okay, so we are running a little behind time, but we can discuss it later.
Yes.
But what I was curious about, it may generate entanglement, but will it generate the way you want it? Is it controllable? Like, can you reach at the desired ground state? So that is what I was wondering.
Yes, I mean, that is for sure. Yes, the grounds. Yeah, we can achieve the ground state, but for that, the annealing procedure has to be repeated many times.
I see.
Okay. Yeah.
Okay.
And this is actually a heuristic method. So there is some trial and error involved here.
Yeah, because temperature is involved here. So
well, it can be. Yes. It can be. Yes. Yeah.
Okay. Thanks. So I have to, although the